Now we are really excited to kick off our plenary session. We have 5 very exciting speakers. We are so happy to have agreed to join us today and share their vision for the future of oceans. It is my distinct pleasure to start by introducing Peter Menocal. Peter is the new president and director of my own home institution, the Woods Hole Oceanographic Institution. We are so happy for Peter to join us because he only just started last week. Peter comes to WHOI from Columbia University's Lamont Doherty Earth Observatory, where he served as Columbia's Dean of Science for the Faculty of Arts and Sciences, and where he founded and directed the Center for Climate and Life. Peter's research in geochemistry and paleoclimate has led to over 100 publications, focusing on how and why past oceans and climates have changed, and their impacts on human evolution and culture. Welcome, Peter. Thank you so much. You can go ahead and.
Okay, yep. Thank you, Seth and Fuddle, and just congratulations on hosting just a fantastic and exciting meeting. I will share screen, and hopefully this will work. Are we live?
Yep, that looks great. Take it away.
Okay, so thank you everyone for this opportunity, and thank you especially to Fuddle and Seth for pulling this incredible meeting together. And thank you, Laura, for the excellent introduction to what I see as one of the most exciting things happening in NSF in my career. I was given the great opportunity to present first in the order today, and just wanted to give some examples of how we are driving convergence in the ocean sciences here at Woods Hole, but more generally, this is an invitation really to the larger community. Let me get this going. There we go. So as Laura mentioned, that there are some really big societal challenges that need innovative thinking. So much of what we do with federal funding today drives so much of the fundamental science and technology that frames our understanding. But when we look at what kind of knowledge and the kind of knowledge creation that's needed to inform solutions, that really requires a different toolkit. But shown up here in the upper left is climate and weather. I mean, obviously I could have picked almost anything on this. This was a snapshot from the North Atlantic just a week or so ago, when we had 7 named hurricane cyclones in the North Atlantic, a record for that date. New York State will be announcing 7 gigawatts of offshore power, and we need to understand how we can deploy those offshore systems and also tie those into the grid. And as we look at each of these examples, one after the other, one can see the call for the kind of cross-disciplinary, really fundamentally integrated nature of knowledge creation that's going to be needed to inform not only the basic questions that are under each of these, but really the scientific and engineering approach. That itself has to be very different than what we've deployed so far. And that's why I'm really so excited to see this opportunity to talk about this. So I thought I'd just give a couple of examples arranged by scale, going from the microscopic to the global ocean, that captures this, this integration of science and engineering and solutions that we're talking about. One example here is looking at microbial ecosystems. So we've been able for a long time to use flow cytometers, which are optical instruments that allow us to filter seawater to identify or take images of microbial life in the oceans. But much of that work had been restricted to optical recognition, manual human recognition of the various microbes that are in the oceans. And a recent advance at Woods Hole, led by Sydney Bachtelder and Joseph Futrell, have been finding a way to use 2 different instruments. One, which is the image flow CytoBot, which is actually a robot or a vehicle that allows flow cytometry as the instrument is passing through the water. And then that collects up to something like 100,000 images per day, each of which has hundreds of specimens on that image. And so it quickly becomes a problem when you're trying to look at multi-year examples. And so what's shown in the red here is a result that just came out this year, where it's using convolutional neural nets, image analysis, to process these hundreds of thousands of images over 17 years. It was 7 terabytes worth of data. So it's a little bit less than the 10 petabytes or so in the IPCC AR6 reports, but we've been able to do this within a week to identify at 90% efficiency. The second at-scale deployment of this convergent thinking is something called the Curious Robot, and this is led by Stuart Jameson and Yogi Girdhar. It's just another example of how one can drive across disciplines, in this case, bringing machine learning, AI, robot development, and then deployment at scale together to inform reef health, coral reef health. In this case, this robot that's built here in the lower right is able to scan the surface of the coral on its own, taking images as it goes along the way. And it's able to direct itself based on a goal function, a target function of looking for corals of interest. And so this just gives you an idea of actually how this, oops, see if we can do this. Come on. There we go. So the problem is really trying to find ways to collect. Oops, come on, I'm going to just try one more time. There we go. So as the robot scans the surface ocean, it looks below and starts identifying corals by type according to training from a human. And so it provides this three-dimensional coverage of, in this case, a large reef surface. And the idea is that if you're interested in, let's say, coral reefs that haven't been affected by a warming episode, the bleaching that occurs during a warming episode, it's a way to actually capture that signal. And so this approach of basically informing the robot to navigate itself to search for corals of interest provides a much greater efficiency. And just to give you an appreciation of the scale that might occur on this actually shows the robot in the ocean right now, or not right now, but that was taken last year in Barbados. You can see the little yellow vehicle there in what is otherwise a very beautiful coral reef system. And it's able to kind of doodle around on the surface of the ocean, collecting all of this information. And it just gives you an idea that if you can connect the intelligence of a human, a scientist, with the flexibility and the compute power of machine learning, you can actually inform much larger spaces. So the third idea really gets out to the largest scale. And this is, again, ways of deploying really large-scale technologies to inform really large-scale processes. So we can, of course, image the surface of the ocean very effectively with satellites, just as we can with the surface of the land surface. But when we start to probe the deeper oceans, it gets to be much more difficult to image both biological systems, but also physical systems as well. And so one of our scientists here at WHOI, Y.T. Lin, developed the Acoustic telescope, which uses a phased array set of hydrophones on radial arms as a way to triangulate in space, that is 3 dimensions in space plus a 4th dimension in time, and is connected to a satellite for real-time information. So you can actually hear and monitor, let's say, migrations of whales. This is actually a design, what the design looks like. It's a bit like an umbrella, but it has a 30-foot radius or a 10-meter radius. And so this just gives you an idea of some of the sonograms that come from that device. For instance, this is a right whale that's passing by, and then a humpback whale as well. And with several of these, one can triangulate not only the position of whales, but also of snapping shrimp and of surface turbulence from windstorms. And for those of you who are in the military sphere, we can also track submarines. This is really a way to essentially make the deep ocean transparent to observe these biologic and physical processes on a basin scale. So I just want to wrap with noting that there are some common elements, this transdisciplinary approach, reaching across disciplines, being radically inclusive, not only by discipline, but also by diversity and inclusion. It's not only the right thing to do, but more diverse communities make better decisions. Also, this concept of use-inspired science for solutions, how to incentivize risk and spur innovation. I give an example of Pasteur's quadrant there on the right as an example that optimizes the need for fundamental understanding and consideration of use. And then the last thing is that we're all in this together. I represent the Woods Hole Oceanographic, and others represent their institutions, but collectively, I would venture to say that we are all deeply interested in finding sustainable solutions for the ocean as soon as we can. And so Laura's comment that we want solutions within 3 years, I think is very welcome indeed. So how research institutions can help, and this is my last slide, is that we need to help build the ecosystems that allow this convergent thinking. In particular, as I was dean, one of the things we learned the most was more collision space, more ability for scientists and engineers and scientists to work together across disciplines. In terms of the research, I think supporting high risk, high value research is imperative. We need to be able to free up time for our grant supported scientists to pursue problems where they can engage in. And last, supporting the next generation. I can imagine that the age profile of many of our viewers today is skewed young. And so we really need to support not only students and postdocs, but also consider promotion and tenure consideration to reflect the fact that not only will you be exceptional at your particular field, but that you're taking risk personally to go after these kinds of solutions, valuing interdisciplinary science. So I will end there and thank you all for your time.
Thank you so much, Peter. That's fantastic. I just want to remind everybody who's watching, please use Slido below the feed here to ask your questions. I'm going to ask a question that did come in. The question is, how can machine learning researchers facilitate smart oceans research with oceanographers?
Right. So actually, this is a space that I was working on in my former institution, not me personally, but this is one of the groups that we supported through the Center for Climate and Life. So machine learning applications are, in my opinion, revolutionizing our ability to pursue really hard problems from really big data sets. That is not only tied to our ability to understand really complex data-rich problems like the one that I showed with the microbe identification, but really it scales up to asking really the biggest questions of the biggest data sets. And so, we're actually running into a problem now is what are the compute engines that are needed to pursue these machine learning questions? And in there, we actually are pursuing industry partnerships where there are some companies, and I can't say which at the moment, but or I shouldn't say which at the moment, but there are some companies that are very interested in partnering with research organizations to work with their accelerated platforms for machine learning applications.
Fantastic. Thank you very much. So I wish we had time for some more questions, but it's 12:28, and so it's time to move on to our next speaker, who will be introduced by Fadl. Thank you very much, Peter.
Thank you, Seth and Fadl. What a great show.